So what I'm going to do now is I'm going to talk about how Java, modern Java that is, combines object-oriented features which have been around for years with the newer functional programming features that have been around for 6 years as opposed to 25 years or so. And we'll talk about the benefits of combining these features. In my experience, the two together are actually quite better than either one in isolation. So the object-oriented features combined with the functional programming features are better than the functional programming features in isolation or the object-oriented features in isolation. And I'll show you some examples here. We're going to start looking at a lot more examples in the upcoming lessons, but this will give you enough to kind of demonstrate some of the key themes, and then we'll look at more code down the road. I'll also spend a little time explaining the when, why, and how to use mutable state with Java, which is sometimes at odds with the more purist view of functional programming as having no side effects, but we'll talk about when and why and how you would use side effects with Java. So I contend that the combination of object-oriented features and the functional paradigm in Java is actually a big plus. If you think about this holistically, it's actually really cool. Why is that, you might ask? Well, the reason for this is that Java's functional features provide certain capabilities that are not well supported by its object-oriented features alone. In particular, the functional programming features help to close the gap, using the word loosely, the gap between a program's intent, the intent that you have, the domain intent, like what requirements are we trying to solve here? That's the domain intent, and the way in which the computations are expressed. And if you read the link at the bottom of the slide about declarative programming, it'll go into this in a bit more detail. So what is domain intent? Well, domain intent is basically the what. It's what problem are we trying to solve? What requirements are we dealing with? So to move this from highly abstract to very concrete, there's a fun example that you can find in my GitHub repository called Image Stream Gang. And we will explore the Image Stream Gang example later in the course. And basically what this program does is it is given a list of URLs, either through a GUI or from a command line or from a file or pre-configured into the program, whatever. It takes a list of URLs that point to images that reside out in the network somewhere, in the cloud, if you will. And it will go ahead and download images that are not already downloaded. So it basically has a cache. And so if the images are not yet cached, it'll download them. And then it'll go ahead and it'll apply various image transforms to filter the images, to do things like emboss or sharpen or red eye removal or whatever your favorite image processing algorithms might be. And after the images have been transformed, then they're stored in parallel. So it does all this image processing using different parallel computation models that are part of the Java ecosystem. So those are the requirements. Now, and so that's basically the what. The how is the actual computations that perform all those different steps. And as you take a look at the code here, this is code that uses the so-called parallel streams formalism or framework. It's part of modern Java. And you can see by reading this, it almost reads one-to-one onto the what, onto the domain intent. So what we say here is we say, in parallel, take the list of URLs and get rid of ones that we've already downloaded and cached. So if they're not already cached, we're going to go ahead and let them be processed. And then we go ahead and we download each of the non-cached images. And then we go and apply the image filters to transform the images. And then we collect the results into a list and then we'll display them. So what's cool about this particular way of doing things is that the actual code, the computations that we implement, are pretty much a one-to-one mapping onto the domain intent. And that's really powerful because once you understand what the domain intent is and once you know how to read the syntax and understand the semantics for parallel streams, it's very straightforward to map these things one-to-one. So the bottom line is that functional programming connects the domain intent together with the computations in a way that's far more intuitive than trying to write all these things in a more classic imperative way with loops and if statements and switch statements and all this kind of good stuff. Now, on the other side of the coin, we have the object-oriented features that are part of Java. And these would include things like classes and inheritance and virtual methods, and so on. And those features are extremely valuable to help structure the software architecture of Java programs. And this is particularly important with larger systems. If you only have 100 lines of code, the architecture doesn't really matter. If you have 100 million lines of code or even 100,000 lines of code, the architecture starts to make a big difference. If you want to learn more about what software architecture means, there's a link at the bottom of this slide that talks about the so-called 4+1 view model of software architecture. And there's these different views. There's a logical view, there's a physical view, a process view, a development view, and a use case view. I'm going to skip over most of the views and just focus on the so-called logical view. And that's the one that's probably most relevant for our discussion here. So this view depicts the subsystems, the packages if you're programming in Java, the namespaces if you're programming in C++, and the various classes and or interfaces that exhibit architecturally important structure and behavior. So if you think about the kinds of things you would expect to see if you created a UML diagram of your classes in your program, that's one part of the logical view of your program. Well, here's a little snippet of such a view. So this is the image stream gang program's architecture, at least a portion of it. And you can see here that we've got a number of different classes that are related to each other using various types of aggregation. In this particular case, we're using inheritance largely. And so what we see here is we have some common superclasses like image stream and stream gang and filter. And the idea of a superclass, as you're probably aware, or an interface, is to provide a foundation for extensibility that can be reused. It can be extended and customized and overridden and so on. And this leads to something called commonality and variability. I won't hold you responsible to know this concept in detail, but it's a very important concept in software architecture, and you can read more about it at the link at the bottom of the page. What we then do is we go ahead and subclass from these superclasses, and we fill in some of the details. So for example, there's a bunch of different ways of writing concurrency and parallelism models to process images in the image stream gang. And we've got a sequential way of doing things, we've got a parallel way of doing things, we've got a asynchronous reactive way of doing things, and so on and so forth. And those are handled architecturally by extending from a superclass and then overriding some of the so-called hook methods to carry out the computations. The computations, of course, are implemented with functional code, but the structure of the overall program is oriented towards an object-based and object-oriented design using inheritance and dynamic binding. And the same thing is also true with the filtering. Once again, we apply inheritance and various patterns like the decorator pattern and so on. So we're using objects and object features to give us our structure, and then we're using the functional features to give us our behavior. So in my experience, the functional programming features, the FP features in Java, are most effective when we use them to simplify the computations within the context of an object-oriented or OO software architecture. And you can see here in this example that when we start using concurrent and parallel programming, these advantages of combining the functional and object-based paradigms is really valuable because it's really easy to think and reason about your program from a functional point of view, from the computations perspective, and then you organize it using objects to structure it properly and make it extensible and easy to understand and make it modular and so on. So this is just kind of demonstrating how the two together are more powerful than either one in isolation. Let's now transition and talk about when, why, and how to use mutable state in Java. So Java is a hybrid language. We've seen that before. It's got functional features. It's got object-oriented features. And so it turns out, even though functional programming really wants you to be immutable and stateless and not share state, there's situations in which mutable changes to shared state are allowed and even encouraged in some cases with Java. And this link at the bottom kind of gives you a nice overview of how functional is Java really? And the answer is it's functional, but there's exceptions to things. So probably the best example of how Java is not purely functional is with its collection framework classes. And undoubtedly, you've run across these before, things like array list and linked list and hash map and hash set. There's zillions of these different types of classes and collections that are part of Java. They're primarily implemented in a non-functional way. In other words, the methods in those classes mutate state. If you have an array list, you're modifying the contents in the array. And in fact, with our first programming assignment, you'll get plenty of experience with this because you'll be implementing an unsynchronized array, which in fact is doing mutable changes to the underlying state, the element data and the count and the size and all that kind of good stuff. And that's okay. So one of the things you discover is, first of all, Java was an object-oriented language way before it was a functional language, so it should be no surprise that it had mutable state and imperative behavior. And even when they modified it to have functional features, there still actually are a lot of benefits to mutable state, especially for the infrastructure pieces like collections. And that's because you can implement things to be a lot more efficient often by using mutable state if you're careful than you can by making new copies of everything and making them immutable. And there's some disagreement about that, but in general, Java does very well because it's optimized nowadays for performance as well as for productivity and ease of use. Having said all of that, you're usually better off in practice by minimizing or avoiding the use of shared mutable state in your programs. So we're kind of grandfathered in with the collections framework. Most of the classes there are mutable as opposed to immutable, but that doesn't mean that you have to perpetuate that in your code. So there's lots of benefits to be gained by applying the functional programming features, the side effect-free approaches in your code, even though some of the Java infrastructure is not designed that way. Now, if you do have shared mutable state in your programs and you're using them in a context where there's concurrent or parallel computations, then you need to be careful and you need to do some additional stuff. And the additional stuff really comes down to properly synchronizing access to this shared mutable state. And there's a whole bunch of ways to do this. One way is to use some of the built-in synchronizers like the synchronized keywords with synchronized methods or synchronized statements. There's also boatloads of different synchronizers like mutual exclusion synchronizers such as reentrant lock, coordination synchronizers like condition object, barrier synchronizers like countdown latch, cyclic barrier phaser, atomic operations like atomic integer, atomic boolean, and so on. And then there's also a whole slew of synchronized and or concurrent collections like synchronized map or the concurrent hash map and so on, or concurrent list. The bottom line here is if you need to share state, make sure you learn how to protect that state. Now, we're not going to talk a heck of a lot about that in this class. It's really not the focus of this class. This class is about not sharing state by using Java's parallelism frameworks. But if you're curious about how to share the state, take a look at the link down below. This is the set of videos and slides and assignments for my companion course to this one, which is called Concurrent Object-Oriented Programming. And that course goes into great detail about all the synchronizers and so on. We will not cover that much this semester, but if you like what we cover here and you want to learn more, I'll be teaching that course in the spring. And you can also see older versions if you go to my YouTube page and take a look, for example, at the link at the bottom of this slide. So that kind of wraps up the overview discussions about modern Java, how it combines object-oriented and functional programs. You will get experience with all this stuff, but of course, we're going to be focusing primarily on how to use the functional programming features, but always in the context of a nice object-oriented design.